Okay, hello everyone. So today's topic of the talks is on class number of number fields. I will try to talk about, it mostly consists of class number, fundamental units, and some concept called relative class number, and some results relating to those things. So we first start with class number. Now the general proper definition is that you take the quotient of fractional ideals, quotiented by principal fractional ideals. But if for the time being, if we are not focusing on that, then you can think of class number as, it is something which measures the failure of a ring of integers to be a PID, or to have unique factorization domain in the element level. Like it has, when you are thinking it, working over the ideals, but not as elements of ring of integers. So actually it has, I also don't know much, but it is a very rich history, the class number of number fields. Many people actually have worked on it. In fact, the original idea of class number, class group, it came even before that idea of ideals came. I think it originally came from when people were working on quadratic forms, and they saw that for consecutive arguments, you are getting prime values from a quadratic forms. And later Gauss, in this 1801, this book, he also gave the idea of class group, class number in the form of binary quadratic forms, which you can, if you transfer, it will be like number fields with even discriminant. Later people actually modified those results and did it for all kind of discriminants. So he actually proposed three conjectures. Two were for imaginary quadratic fields, one was for real quadratic fields. Imaginary quadratic fields, both the results have been proved, like people like Hilborn, and then later I think Stark, Baker, and very recently like 1985, I think Goldfield, Gross, Jagier, all of these people were involved, and they proved first two conjectures. Those conjectures were like, first was if you have a imaginary quadratic number field, and the discriminant if tends to minus infinity, then the class number tends to infinity. And it's the kind of growth of the class number thing. And the second one was he actually gave a list of class number, a list of imaginary quadratic fields with a given small class numbers, and he thought, he conjectured that that is the final list. So people actually proved that, all those two results, but the real quadratic, for the conjecture that he gave for real quadratic fields, it is still very much open. It was that he conjectured that there will be infinitely many real quadratic field with class number 1. Now this class number 1 thing is very much adored because of the fact that it gives the desired unique factorization thing in the elementary level. Later also, when people are solving Fermat's last theorem, even the basic point, like when you have x to the power p plus y to the power p is equal to z to the power p, the natural idea is that you just made that x to the power p plus y to the power p, you factorize it like x plus, in the pth cyclotomic field, you just write it like x plus zeta y plus x plus zeta to the power iy, that's product kind of thing. And people, it would have been good if if that product, it is something like a product of these many elements is equal to some z to the power p. So it would have been better if we could have said that each of these elements is a power of some number p, which was true in an ideal level, but not true as an element. So those kind of problem that people are facing made the concept more important to the maths community. So this conjecture that the existence of infinitely many real quadratic fields of class number, it was still open, and it was really tough. So later in 1856, in a paper, Dirichlet actually gave a concept called relative class number, which was similar kind of a concept I will define very shortly. And he asked a similar kind of question as like the third conjecture of cause. So he asked about the existence of infinitely many real quadratic fields with relative class number as 1 for some conductor f. I will define what is conductor and all those things now only. So the definition of a relative class number of a real quadratic field is nothing but the quotient of, means you take something called an order of conductor f, which is this z plus, you just think about class number of this ring and quotient it by the class number of the ring of integers. And Dirichlet actually asked that, inquired about the fact that whether there will be infinitely many real quadratic fields with relative class number as 1. So in his 1856 paper only, it consists of many useful results, like which actually over the years people use those results and try to find whether this happens or not. So the most important result was this formula of, formula for finding the relative class number, which is this, where the psi f is this factor and theta f is the smallest positive integer, such that the fundamental unit to the power that theta f will be in that ring, that order. So fundamental, I forgot to tell about fundamental unit. Now fundamental unit is, again, it's a famous theorem by Dirichlet, which is called Dirichlet's unit theorem. It says that the ring of integer of a number field, it explicitly gives the formula of the rank of that, means how it will look like. Like he said that the rank of the unit group will be r plus s minus 1, where r is the number of real embeddings, 2s is the number of complex embeddings. Like Sujata ma'am mentioned that if you have a one complex embedding, then the conjugate will be another. So 2s is the number of complex embeddings. So r plus s minus 1 will be the rank. So now you can see that for quadratic and for cubic number field, it's really good, because you can say that the fundamental unit, because like for real quadratic field, it has r equal to 2, s equal to 0. So r plus s minus 1 will be 1. And for complexes, r1, s1, so again 1. So there is a particular element such that all other units will be the power of that element. So that element is called xi m. Like here we are for quadratic fields, so we are calling it xi m. So again later also we will do for cubic number fields, again we will use that the fundamental unit concept. So now, so now we are trying to, what we will try to see now is that to find whether that assertion or the question that Dirichlet inquired about, that whether there exists infinitely many real quadratic fields with relative class number 1 or not, we will see that that was actually true. So we will start with assuming this is the form of the fundamental unit. Means obviously there are some certain, here only we can, it's not always like alpha and beta, alpha naught and beta naught, you will find them as integers, but for the time being you can assume they are integers. Like their cases may arise that it will be some by 2, because ring of integers, it's not always like, ring of integers of a real quadratic field q root m, it's not always like you will find it as z root m, but in some cases, like when m is 1 mod 4, you will find that it will be something like, in denominator you can find a 2. But for proofs are almost similar, so you can assume that alpha naught and beta naught are integers. Now you can see that from the previous formula, like here, if q is a prime and q divide beta naught, then obviously that theta f will be 1. It's just via definition. And if q is a prime and q divides m, then this whole value will be q. So here, first one I already said. And now, so if there is a square free integer m that does not divide this beta naught, then because m is square free, you can find a prime q such that it divides m, but it does not divide beta naught. So what will happen is that you will find that the psi q is q, but theta q will not be 1. But because that relative class number is always an integer, that was also proved by Dirichlet. So in that formula, you can say that theta f will always divide that psi f thing. So if you have something in the numerator as a prime, so there is no other option for the denominator apart from being it 1 or q, means or that prime. So if you know that it is not 1, so it has to be a prime, it has to be that prime, and then the relative class number will be 1. So as I said that now I will state some results one after another which actually will prove that give an affirmative answer that there exist infinitely many real quadratic fields with some conductors such that the relative class number will be 1. Like similar results has been proven by Professor Mollin, Richard Mollin, but his paper actually consists of, means obviously his paper consists of, it's a good paper in the sense that it has too many references from whatever people have done over the years, means he used all those results, but you can find a simpler proof like we are going to state here. Like if we use this theorem that if P is 1, means this can be proved that if P is 1 mod 4, which does not divide M, then the relative class number for conductor is not 1, but this part is not important. This part is actually will give that relative class number will be 1. So it says that if P is equivalent to 3 mod 4 is an odd prime not dividing M, then the relative class number for conductor P is odd. Now you see, if I have a real quadratic field with such that the norm of the fundamental unit is -1, so just this statement gives you that -1. If there is a prime P that divides M, it will give you that -1 will be a quadratic residue. So from there, if you see that 3 can never divide that M if you have such a real quadratic fields. And then if you take the conductor as 3, from that formula of Dirichlet, you will find that the numerator can only be 2 or 4, just putting that value 3. So if the numerator is 2 and 4, and if you already have that result that for P equivalent to 3 mod 4, the conductor is odd, so the only possibility it has to be 1. Because if you have something which has on the left hand side a fraction whose numerator is 2 and 4, 2 or 4, and the right hand side you know that the value that you will get is odd, so the only possibility is that the left hand side is 1. So I will just try to give a sketch of proof of one part of this proof, or one part of this result, because otherwise it will be too long, but other parts can also be proven, means it's almost in the similar way. So what we will do that we will just try to give a proof for P equivalent to 1 mod 4 when this happens, that M is a quadratic residue mod P. When you see that D and M, it does not matter because D is the discriminant and it is a discriminant of a quadratic field. So D is either M or 4M. So 4 anyway is 2 squared, so it doesn't matter. So what we see is that as we already assumed that xi M has, we already assumed that fundamental unit has norm 1. Now if you have P equivalent to 1 mod 4, then you see that P minus 1 by 2 is even. So if you took a power of that fundamental unit as this, it will has norm 1 because this thing is even. So its inverse will look like this. Little bit calculation, it does not directly follow, but you can see that means you add those, means up to this it's fine, you add those two things and you find this, and then this thing will will belong to this POK. Because what happens is that this part under the bracket, that belongs to this POK. So that follows with a little bit calculation, not directly, but it happens. So once you have that, you find that the 2 beta 1 root M, it belongs to this, but P neither divides 2 nor divides, nor it is coprime to M. So the only possibility is that P divides beta 1. And now if you have this, you will find that this theta f that we have described earlier, it will always be a factor of P1 minus 1 by 2 or P1 minus 1 by 2 itself, that doesn't matter. But what will happen is that if you have that it is a factor of this, numerator is nothing but P minus 1. If you have a prime P that does not divide M. So the denominator is a factor of this, means the relative class number it cannot be 1. It will be at least 2 or a product of 2. So that's why that theorem follows. And now, as I explained already, that if you assume that theorem, you will find that the relative class number for conductor 3 must be 1, because 3 is a prime 3 mod 4. And then there is a result that, so I mean it also follows easily, because now if you take any prime which is of the form 1 mod 4, what will happen is that it will always have norm minus, means q root p will always have norm minus 1. And because it is a prime of 1 mod 4, 3 will not divide that thing. And now having these two, you will find that, means combining these two result, you will find that the relative class number will be 1 for that conductor. In fact, a proper theorem can be given about necessary and sufficient condition when the relative class number 1 cannot be 1. But yeah, I am not talking about that either. So I will go fast and talk about this. This is about a fundamental unit of a cubic field and its class number. I have already talked about a fundamental unit. So again, that this was the Dirichlet's theorem, and so the main result of this area was this, that if q not equal to m be a prime that ramifies in this, then you can write q you can write the fundamental unit or its square as alpha cube by q for some alpha. Now it follows easily because you have a prime ideal, you are assuming that the class number is not divisible by 3. What will happen is that if you know that a prime ramifies in the extension, then it will be some ideal cube. Now if it is an ideal cube and you know that the class number is not divisible by 3, so this follows that that ideal will be a principal ideal. So it will be like that prime into some fundamental unit will be some another element's cube. So from there it follows. Similar argument for quadratic fields gives you this proposition, and this result is very old. The result that I am going to tell you, this result is very old. This is one part of the classical result, that whenever you have a real quadratic field with even class number, then it is an if and only if condition, that the real quadratic field has even class number if and only if the discriminant is divisible by at least more than or equal to 3 factors. So that follows easily from that argument. Means it's a very straightforward, but it only gives the sufficient part. So this is the sketch of the proof, that if you have more than 2 factors, then p, pq, if they are the factors, pq are the factors, and you can see p and pq both ramify, but none of them is a square. But from using that result, you will find that root q will belong to k, which will be a contradiction. And now I will just show you some theorems with proofs in examples like they happen. So this is the theorem. Actually, this theorem, this corollary, it agrees with a very old, I think 1970 result of Frank Garth. So this result actually, he proved using extensive Galois theory, but you can get it, means the result can be proved using that concept that we have said, that using that also you can prove. So these are some examples which actually agrees with this theorem. And also this is another theorem regarding the congruence relation satisfied by the fundamental units. And you can see that this is another table where you can see that if the congruence relationship is not satisfied by the fundamental unit, then the class number will be divisible by 3, which we actually assumed. So we will end with this. We also have only 1 minute. So this is just, I will just say and then go through the slides. It's about elliptic curves and unramified quadratic extension. So as we already know, it is already known from class field theory that the ideal class group is the Galois group of the maximal unramified abelian extension. Now what happens is that even if you don't get a maximal thing, but if you get an unramified abelian extension, so it will sit inside that thing. So you will not find the ideal class group, but you can say about divisibility of that ideal class group, because the Galois group will sit as a subgroup of the whole thing. So there are actually too many results about people actually tried many mathematicians tried about finding divisibility of class number criteria. So like Ragnar Soleng, he gave a very, I think I have a typo here, but he gave a very interesting proof where what he did is that he took a torsion group of an elliptic curve. I'll just take 1 more minute. So he took torsion group of an elliptic curve and put it inside in an ideal class group and show that that is a subgroup of an ideal class group. So from there he got a divisibility criteria, not exactly the ideal class group. Similarly, ROC Sato and Franz Lemmermeyer, they also calculated. So our results is inspired by Lemmermeyer. So this is the main thing, that if you have a torsion, if you have a non-torsion point in an elliptic curve, then you can construct bi-quadratic fields like this, which will have even class number. So I will just, that sketch of the proof is all, means this part is what Sujata ma'am has mentioned in the first lecture, that this is the duplication formula. Like it's not very, means it is P plus P, but not very general P plus P. So if you have R, S, T and T, it will look like this. So using those and these results also, like if you define an alpha which will be some S plus root mt cube, you can find that alpha will be some ideal square. And from there you will find that the extension is quadratic and unramified at all primes. Like infinite primes you don't have to bother because everything is real, but or if it is not real, then it will be imaginary even before you have to bother about those. But finite primes, too, you will make it forcefully unramified by considering some conditions. Other finite primes, you can follow from here that they will be unramified. So from there, it will follow that. And also you can show that an infinite family of such bi-quadratic fields can be constructed. Yeah, so that is this. So I think these are the references that I have used for this talk. So yeah.
Just like n equal to 1, given any number, it's unknown whether there are, given any x, it's unknown whether there are infinity field of that class.
That class.
So like 2, 3, something, does it help?
In for class number or?
So corresponding question for, you are doing for relative class number.
Yeah.
2, 3,
yeah, there are results, like even
your method extends.
Even that paper only, that this paper only have results which says about, yeah, I think this paper only has results which talk about that infinitely many class of relative class number 2. But there are some glitch, like we have assumed some infinitude of Marcin primes or Sophie German primes. So from there, means, yeah, but there are results, like most of the results relating to these people used continued fractions, like Mollin's paper also, it uses continued fractions because the fundamental unit can be seen as a part of, you can explicitly construct it from continued fractions. So they are also results, like other than 1.